Now that we've solved the simple harmonic oscillator in the ideal system, a mass on a spring, let's try to discover how that mathematics can be generalized to apply to almost any oscillating object. First, we're going to do this by considering energy. Energy has two parts in the mass on spring system: kinetic portion, 1/2 mv squared, and a potential energy portion, 1/2 kx squared. And in these expressions, remember the velocity, v, and the position, x, are changing over time. They're functions of time. So the kinetic energy, the potential energy are not constant, but their sum is, because the spring force is conservative. So E equals Ke plus U will be a constant. Let's see how that works out in the mass on spring system. I'll use the general solution in terms of amplitude and phase because it's easier to square the x and the v. To get the kinetic energy, I take half the mass and multiply it by v squared. I'll write the omega squared first, and then the a squared. Then there's the square of the sine function, which varies over time but is always positive. So the kinetic energy is largest when the sine function is close to 1 or -1. That's when it will be moving the fastest. To get the kinetic energy function, I'll take 1/2 the spring constant times the x function squared. That will just be a squared times the cosine squared of omega t plus the phase. So the potential energy is also varying with time, and it's large when the cosine is either plus or -1. So remember, the cosine is related to the position. So when the position is maximum or minimum, the spring is highly stretched or highly compressed, and the potential energy is the largest it gets. The velocity is 0. On the other hand, when the velocity is close to 0, the spring is nearly at its equilibrium length, and the kinetic energy is large. So we see this sort of interplay here, where potential energy is large when kinetic energy is 0, and kinetic energy is large when potential energy is 0. Let's see how they actually add together to make a constant. Here's the kinetic energy term. On the next line, I'll write the potential energy term. It looks like we might be stuck here. There's so many variables. But remember that there's something else going on in the harmonic oscillator that relates the angular frequency to the mass and the spring constant. They're not all independent. Omega must be equal to square root of k over m for this to be a solution. In the energy expression, we see omega squared appears here. So omega squared could be replaced with k over m. Then the m's would cancel each other out, and we would end up with just a k. Now, both terms look similar. They have 1/2 times the spring constant times the amplitude squared. So that can be factored out. The remaining trig functions, sine squared plus cosine squared, always add up to 1, no matter what argument or time they're evaluated at. So this term can be canceled to a 1. And we found that the total energy of oscillation is just 1/2 times the spring constant times the square of the amplitude. Because of this relationship here, we can also write this as 1/2 m omega squared a squared. Since the kinetic energy is 0 when the velocity is 0 and the position is a max or min, when x is at a max or minimum, the total energy is equal to 1/2 kx squared. And when the position is 0, the velocity is at a maximum or a minimum. Either it's moving to the left through 0 or moving to the right through 0. So when the position is 0, the potential energy is 0, and all the energy is then in kinetic. So when the object is at its maximum or minimum speed, the energy is equal to 1/2 mv squared, because v is proportional to a times omega. So this a times omega here is v. And at the max or min, it would be v squared, 1/2 mv squared. All right, so the total energy is really only dependent on the spring constant and the amplitude, or in other words, the spring, the mass, its frequency, and the amplitude squared. Now this tells us a bit about how these oscillations get carried out. The energy transforms back and forth between kinetic and potential. And if we think about one of our previous topics, I promise you we don't study anything for no reason. If we think about our previous topic of potential energy functions, remember that when we had a minimum locally in the potential energy function, we said that motion with an energy of E could cause what's called turning points. And the object with this potential energy function would move back and forth between those turning points. The motion was said to be bound and have a binding energy that was required to get away from x0. If the energy is only a small amount above the energy at the minimum, then the object is bound to move in small oscillations around the location x0. We said that it was in state equilibrium. Well, we can actually now prove this statement mathematically. If the position of the object is near to this point x0, then the potential energy function as a function of x can be envisioned as a function of, instead of just the x coordinate by itself, to be evaluated at the sum of the minimum position and some small deviation. So our x position is nearly equal to x0, but has some small deviation back and forth around there. So the difference between the x coordinate and x0, the position of the minimum, is small. And if we've, if you've taken some semesters of calculus, you may recall this, but it's no problem if you don't. But when we have a function that is evaluated at some central position plus a small deviation, we can expand that function in what's called a Taylor series. Right? If the x minus x0 part was incredibly small, 0, then the answer here would just be to evaluate u at x0. If we considered the next largest effect, which would be x0, x minus x0 being somewhat large but not huge, then we could approximate this function by a line, and we would get a term that's linear. So plus the slope times the distance from that spot. But if x0 is a minimum, at a minimum, by definition, we have zero slope. So this term, if we expand about a point of stable equilibrium, is always zero. And what that means is we have to find out what the next term is in the Taylor expansion to get anything non-trivial. The next term in here is to approximate this minimum position as a parabola. And the expression for the parabola is 1/2 times the second derivative of the potential energy function, evaluated at x0, times the distance from the equilibrium spot, from the minimum, squared. Now there are, of course, more terms in this Taylor expansion that depend on the third derivative and x cubed, fourth derivative and x fourth, but those are not necessary to get an interesting result. If you go to graduate school in physics, you add those on slowly, one at a time, and see what kind of complicated modifications they make. But approximating it as a parabola is good enough for our purposes. Let's take this second derivative, evaluate it at x0, and give it a name. For reasons that will become obvious in a moment, we will call this derivative, evaluated at the minimum, k. This is just some constant, right? Even though it's a derivative, it's just some constant. There's a curvature to the function here. You get that concavity value by taking the second derivative at that spot, and you call it k. So it's at a specific spot, so it's just a constant. So what this means is that our potential energy function has essentially been approximated as a constant value, u0, plus 1/2 times this k value, which we just defined, times the displacement from equilibrium squared. And that means that the force function that goes along with that, which is the negative derivative of the position, is equal to minus k times the displacement from equilibrium. Now that's a very powerful result. It says that no matter what the potential energy actually comes from, if the motion is bound up near a minimum value in the potential energy, in a potential well, that near that minimum, the force acts approximately as if it was coming from an ideal spring, with a spring constant equal to k. So this allows us to take all sorts of physical problems, swaying skyscrapers, vibrating tuning forks, and just interpret them as masses on springs. So this is the story for potential energy. If we have a potential energy from any source, we take its second derivative, evaluate it at the minimum part, and that gives us what we call the effective spring constant. The motion of the system will be completely identical to the motion of a mass on spring idealized frictionless oscillator with a spring constant of k. Now let's take a look at the other side of the story, which is the kinetic energy. Now, in the mass on spring system, we wrote the kinetic energy as 1/2 mv squared because it was just the normal type of kinetic energy that arises from a mass moving. But as we've seen in our study of rotation, there can be other forms of kinetic energy due to rotation, or kinetic energy due to electrical charges, or in other future branches of physics, different types of kinetic energy. And the kinetic energy will always depend on some type of speed value. Whether this is the actual speed of a moving object, or whether it's the speed of electrons through a coil of wire, or whether it's the speed, relative speed between two atoms in a molecule. There will always be some speed value on which the kinetic energy depends. And we can think of the kinetic energy then as a function of speed. Now, playing off our discovery with potential energy, we can also try to determine how this kinetic energy function, which may be very complicated, can give us an effective mass. So here's what we'll do. We'll take the derivative of the kinetic energy function with respect to the speed value, velocity. Divide that. This will give us, let's see, mv. That's the correct derivative. There's a little hint for you. That's momentum. Ding, ding, ding. And then let's take the second derivative of the kinetic energy function with respect to speed squared. This will give us just m. So this gives us the right mass for an actual motion of mass. But in other scenarios, this derivative of kinetic energy with respect to velocity, second derivative, will give us some constant value, and we call this the effective mass. So no matter what the system is, how its potential energy arises, or how its kinetic energy arises, we can always define an effective spring constant and an effective mass and the angular frequency of the oscillation will still be predicted by the result for the ideal mass on spring oscillator. An angular frequency equal to square root of k over m, or a period equal to 2 pi square root of m over k, where m and k are the effective values. Let's see how this works out in practice with some systems that are not simple mass on spring. I'll write the definitions of the effective quantities up here on the top right. Let's consider the system called pendulum. So a pendulum is a mass on the end of a rigid string of length L. It's attached to an immovable ceiling, and generally we describe its position by an angle theta, which is not a conventional angle, but rather measured from vertical downwards. So an angle of theta equals 0 means that the mass is just hanging straight down. We do it that way because then the equilibrium angle theta 0 is just when the mass hangs straight down at rest. So theta 0 equals 0. Theta will now play the role of our x coordinate. It's not symbolized by an x, but it tells us something about the displacement of the object from equilibrium based on how it's allowed to move. Our potential energy function here is one that we've calculated a bit before on some homework problems. Essentially, it's a gravitational potential energy equal to mgy. But the y coordinate here by geometry is equal to L, the length, times 1 minus the cosine of the angle. If you draw a triangle in here that's right, this angle is at the top vertex, and the adjacent side is the horizontal leg. The adjacent side to that angle is this vertical leg, which is equal to L cosine theta. Of course, the distance all the way from the top to the bottom is equal to L. So the height of the mass from its minimum position is y, is L minus L cosine theta. So that's our y coordinate. Now the graph of 1 minus cosine theta makes our potential energy look something like this. Of course, this has a minimum at 0, but it's basically a cosine function with a minimum at 0 and a maximum at 2 mgl. Right? A whole diameter away up at the top is the max. But near the minimum, this potential energy function has a local minimum. It has a divot here, a well, right? And so we can approximate that as a parabola by doing this second derivative. So u will be equal to, exactly equal to mgl times 1 minus cosine theta. The u0 value is when we have theta plugged in at the point of the minimum. So that's just going to give us 0 because cosine of an angle of 0 evaluates to 1. 1 minus 1 is 0. Our second derivative, though, now with respect to theta, because that's acting as our coordinate, we'll have the mgl in front. The cosine, the 1 will get turned into 0 by the first derivative. The cosine will turn into negative sine. So we'll get negative times negative sine in the first derivative. So sine in the first derivative. And in the second derivatives, we'll go back to cosine. So cosine theta with a positive in front. And if we evaluate this at the point of minimum potential energy, theta is 0. So this just evaluates to mgl. So our effective spring constant here for this system is actually mgl. The forcing towards the bottom, the forcing comes from gravity, so it's not unexpected to see gravity in there. Now what about our kinetic energy? Well, we still have a mass on a spring. We still have a mass moving here. So it's 1/2 mv squared. But our position coordinate was the angle theta. So our velocity, the actual speed of this mass is equal to the rate of change of the angle multiplied by the radius. So ml squared times the rate of change of theta. I don't want to call this omega right now because that would be very confusing with the angular velocity that we'll get later on. So I write this as d theta dt here, but this is really our velocity parameter that we will use for the derivatives. So I'm going to introduce a new symbol for it, which is theta dot. This is equal to d theta dt. So then our kinetic energy function is equal to 1/2 ml squared theta dot squared. And when I do this derivative to find out the effective mass, I'll be doing the derivative with respect to theta dot. So one derivative would give me ml squared theta dot, and the second derivative with respect to this velocity parameter would give me ml squared. So the effective mass of this system is equal to ml squared. It depends on the length, and it depends on the mass of the object. Now let's use these two results to calculate the angular frequency in this system. This is what I save the symbol omega for. It will be the square root of this effective spring constant, mgl, divided by this effective mass, ml squared. And notice for this pendulum, something somewhat magical happens. Right? Since the mass appears on both terms here, it cancels out, and we end up with the square root of g over L. So the angular frequency of the pendulum depends only on the length of the string and the acceleration of gravity. Right? The period is just 2 pi L over g. But this has made pendulums a favorite device for keeping time because we don't have to worry about how heavy the bottom is at all. We just have to worry about how long our string is. And it's very easy to adjust the length of the string rather than to set a precise mass and keep it that way all the time. So this is why all manner of old clocks involve things that swing back and forth. That gives us a steady time as long as we keep the length steady. And even if you've ever used a cuckoo clock or adjusted an old grandfather clock, you know that if it's running fast or running slow, you change the length of the string or chain that holds up the mass that swings back and forth. So there's our analysis of the pendulum in terms of energies, effective mass, and effective spring constant, and we get the correct answer that can be obtained in several other ways as well. All right, let's do one more example that uses this idea of energies to calculate the frequency and period. So this is a similar kind of pendulum as the last ideal pendulum, but this is called the physical pendulum. So the previous pendulum involves a massless string which has a point object at the bottom. And we should expect from our work on rotation that no object is really a point object with all its mass concentrated at just one position. Things usually have some size. So the physical pendulum takes account of that by having a large arbitrary shape pinned down at one point by an axis of rotation, so an axle goes through it, and then allowed to oscillate back and forth under the effects of gravity. What's going to be important here is two things. One, the position of the center of mass, which I'll mark with an X, and center of mass, and the moment of inertia of this arbitrary shaped object. Now, of course, since the shape is arbitrary, we can't calculate numerically the center of mass or the moment of inertia for this discussion. But if we were told what shape it was, say a cylinder or a rectangle, then we could find these out and go through all of the numbers. But right now, let's just see if we can predict the period that this would oscillate at. You know, whenever the center of mass is not hanging straight down, it's going to generate some torque on the system and cause it to move. So let's do this in terms of energies, though. Right? The potential energy of gravity will act as if the entire object is concentrated at the center of mass. That's the nice thing about center of masses. So we'll call this distance L. And now we realize that L is the distance between the center of mass and the axis. Right? So the gravitational potential energy will once again be mgl 1 minus cosine of theta. Where theta is the angle between there and straight down. And now L is the distance to the center of mass, not to a single bottom point or anything like that, to the center of mass. So this is going to give us the same kind of spring constant that we got in the previous example. The cosine just gets derivative twice and turns back into cosine, so it's going to be equal to mgl for the effective spring constant. Here, the kinetic energy is the one that's more interesting. We have an energy due to rotation. So, back in the rotational motion section, we would have said, oh, kinetic energy of rotation, 1/2 I omega squared, right? I want to save the symbol omega now, though, for the angular frequency of the oscillation, not the instantaneous rotational velocity of the object. So again, I'll use this symbol theta dot to represent the time derivative of the angle. Now if we take our derivative of kinetic energy with respect to theta dot, we will get just the moment of inertia. So that's quite pleasing. The moment of inertia is the effective mass for a physical pendulum. So we can now take those effective spring constant and effective mass and predict the formula for the angular frequency of the object. So mgl over moment of inertia, where the square root is the angular frequency. The period is 2 pi times the square root of moment of inertia divided by total mass times the acceleration of gravity times the distance to the center of mass. So it's a very slick way to find out the oscillation frequency in these systems that are far removed from simple mass on springs. As long as we can find out something about how their energies behave, we can predict their frequency without going through all the nitty-gritty details of force and torque and components and that sort of stuff. So let's do a let's use this now. Since this was so quick, let's actually determine a specific shape now and find out its frequency. So here's a favorite one to do. We'll do a thin hoop of radius r. So like a hula hoop or a ring, and it's got a pole through it or something that's holding it up at the top, and so it can kind of swing back and forth on there, rolling back and forth while maintaining contact at the top. Right. The radius of this is r, and let the total mass be m. So for our formula for frequency, we need to find out the value of L. Remember, L was the distance between the axis of rotation here and the center of mass of the object. It's quite clear for our thin hoop of radius r that the value to use for L in that formula is just the radius of the hoop. That's the distance between the axis of rotation and the center of mass. So distance between axis and center of mass. Right? The total mass is just specified as m, but we do need to figure out the moment of inertia of this object. Now let's be careful because we might know the moment of inertia for a thin hoop of radius r, but this thin hoop is not rotating about its center of mass, right? It's rotating about a point that's displaced from the center of mass. So we actually need to use the parallel axis theorem to get the correct moment of inertia for this object with this axis. Remember that the parallel axis theorem says the moment of inertia about a specific axis will be equal to the moment of inertia of the object about its own center of mass, plus an additional term due to the displacement from the center of mass. So we'll have mr squared. For a thin hoop, the moment of inertia is just mr squared itself. So we actually get two contributions here which are identical and make the moment of inertia equal to 2mr squared. If we take this information and now substitute it into the formula for the period, we will get 2 pi times the square root of 2mr squared, that's I, divided by mgl. And again, we see we can cancel the masses. The value for L to use was R. And then we can cancel one factor of R. So we end up with a formula here, which I'll clean up a little bit. The period of this hoop swinging on its a point on its top is 2 pi times the square root of twice its radius, or its diameter, divided by the acceleration of gravity, g.